one thing going on and just energy. Okay. So here is a further analysis. And this one is going to make you famous. This is the one that I've come up with. Oh, but it's gone out of fashion. Work is the ATM of physics. Okay? Physics. It's how you exchange in joules. Okay? So you know what an ATM machine is? Automated teller machine. It's when you can get this cash. Right? This is real money. This is what it looks like. Look at this. Russians are way overpaid. Look at that. 4 singles. This is where you get cash. If you want the true 80s, SID 80s experience next year, I went to college before there were even ATMs everywhere. Forget not having other things. There were no ATMs. So on Friday, you went to the grocery store. Have you written a check before? You write a check and you'd write it to cash, and you'd give it to the grocery store person, and they would give you cash. And then you had cash, and you had fun on the weekend, and when you ran out of cash, you were done. And then that was the end of the weekend. That was over. You had no other access to your money back then. You couldn't use credit cards at bars back then. They didn't. Well, the grocery store was like a bank, and they had tons of cash. I mean, there was a special aisle for cash. Like, there's a place to buy your groceries, and then there's the window where you just get cash. Yeah. So SID 80s next year, do that on Friday afternoon. Then you have the legitimate experience, not whatever you do. Okay, so ATM of physics. Let's see. What we're going to do is, this is the basic idea. We're going to exchange. So to do work, you push with force F through displacement R. Force F through displacement R. Okay. So what we're going to do is give you sort of 3 versions of the mathematical definition, and we'll do a little example for each one. Because it's kind of like torque. There's a few ways you can calculate it, depending on how difficult your situation is. So let me just show you all 3. So first is, remember we physicists like to say in general. Okay, in general is Latin for, don't write this down. Okay, so in general, the work is the integral between 2 positions, say R1 and R2, of the force dotted with the change in position. Okay. Now look a little bit, remember impulse was how the force is times the dt, how the force is a function of time integrated over time. This is the force as a function of position integrated over position. So if you have a case where a force varies, you actually have to use the integral. Okay, we'll maybe do 1. Okay, usually though, you might have something more like this too. If your force is constant, then you don't have to deal with the integral. Right? If it's constant, then the integral of dr is just r. So then you get the work is F dot dr. So you do have to deal with a dot product. Okay? So I think when we did vector intro, I don't think we did dot and cross product. I think the plan was to do them as we go. Okay? So this is just a way to multiply 2 vectors, and dot product is the one where, say you have an object that goes through a distance r, but your force is in the same direction, so you're pushing like that. The real answer is you just want the component of the force along r, and that's what the dot product is. Okay? Dot product gives you a scalar, right? The dot is 2 vectors make a scalar, and it's just the component of the parallel component of the force parallel to r. And this is not a detail. The whole point is. Okay, so you can write it that way if you're in formal vector world, or you can write it this way. Remember how for torque we had like the perpendicular component? You can also see it written like this. It's just the parallel component to r. Take the force, find the component parallel to r, multiply that by r, the displacement r, and that would be it. That's a little bit easier to deal with. Or if you're in polar vector world, you could write it as the magnitude of the force times the magnitude of the displacement times the cosine of the angle. definition of dot product of two vectors, magnitude, magnitude, cosine. Going from F to R. Okay, so in some problems you would need to do that, right? You might not be pushing exactly along the force. And then number 3 is the best, is when the force is constant and parallel to the displacement. Oh yes, then it's just F. It's constant, you don't have to do the integral. They're aligned, theta is 0, cosine 0 is 1. The component F along R is just F, F R. These are all the work. Okay, so let's look at a few cases of using